because the most prominent members of the image are bell peppers themselves. Right, so that's the basics of employing a deep learning model. So a lot of the functionality that a lot of developers are doing now is taking pre-trained models and employing them into their applications. Not all developing your own is a wholly separate application, wholly separate workflow than just employing it. So if you want to employ it, it's simple enough. Load them, load the model, load the data, uh, feed the data to the model, and then get the output. That's essentially what you want to do, what you want your end users to be able to do with this model. So you see this in uh, OpenAI's ChatGPT, where you're able to give in a row of text, and the large language AI model is then able to give you a row of text uh, as an output. So here, in essence, we're creating functions that take input from users and then give a specific type of output based on what we've trained it on. And hopefully that wasn't too hard for anybody, and we can proceed with our work here. So that's how easy it is to get started with deep learning, or at least using a network should be that simple, right? So 6 lines of code, it's not really that hard to do. The next step would be a lot higher. So we now know how powerful networks are. The next step that we want to do is be able to uh, create our own, right? So what if we have a new problem and the networks that are published or that we have available to us don't really try to answer it, right? Well, that's where a lot of uh, two approaches can happen. So you can actually build networks from scratch or use pre-trained models. We use, for example, a pre-trained model named AlexNet, or you can, and we have a lot of those models already within MATLAB. So if you're getting started, VGG, GoogleNet, AlexNet are very good. They're very simple, low cost models that are powerful enough. For object detection, we have ResNet, DenseNet, Inception. And if you want something that are lightweight and computationally efficient, SqueezeNet, ShuffleNet, and MobileNet are available as well. You can look at the list of models when I send this material to you. Or if you're collaborating with some other with other researchers, or if you see a research paper that you're interested in, and they're working in some other platform, whether it be Keras or TensorFlow or PyTorch, uh, you can actually import all those models in MATLAB. So we now have Keras Importer, Cafe Importer. Recently, I think as of 2023B, we now have importers from TensorFlow and PyTorch as well. So you don't have to go through the ONNX network anymore, or the ONNX standard anymore, and jump directly to MATLAB. Right. So the way that works is you can download the PB files, or you can download the exported model file, and then import it into MATLAB through the functions that we have. Actually, you can actually do this from within the Deep Network Designer, as we'll see it later. But in any case, regardless of which which platform your collaborators are in, or what you are previously using, if you want to continue developing within MATLAB, uh, the the process is not fully not no error, but at least there's not as much friction as having to recode it from scratch. And sometimes pre-trained models aren't always enough. Sometimes the problem is too specific to you, or sometimes somebody just doesn't have the model yet, or this problem is so new that you're the first one tackling it, or there's not a lot of people publishing their work. And that's where AI modeling comes in, right? This is where you want to choose the model that you're doing by designing it and being able to tune it. So here, this is where I'll discuss what the different layers architectures are, particularly what are the layer architectures that are very specific to convolutional neural networks. Uh, and this is because they're actually very powerful network architectures that are able to that are very good at classifying images. A lot of the examples today, in fact, almost all of the examples for the for today are going to come from convolutional neural networks because there are a lot of image classification problems. So I'll go through the three main important ones. The convolution layer, for which the network architecture is named, and then going through the ReLU layer, which is a relative lapse unit layer, I think, and then the max pooling layer, which are two operations that just allow you to uh, uh, normalize your data as well as for compress your data. So this is supposed to be a video. Okay. So uh, convolution is basically an operation that takes an image and tries to search for specific patterns. So the first thing, the more common image classification example, or the most basic image classification example, is what do you call this? Digit classification using in images. So, for example, if you have a black and white image of hand drawn images, on pixels, on the pixel scale, this is what a zero would look like. You can imagine that sometimes this zero might be slanted, or this zero might be a little bit longer or a little bit shorter, depending on whatever variation in handwriting is present. But more commonly, you will see these types of patterns or three by three patterns within that image, regardless of the variation, as long as it's not too drastic, as long as you can recognize it as a zero, right? So the slants, the opposite slant, horizontal and vertical lines, you'll see it here, and this sudden shift should be present within the image. Right, so uh, this pattern should result in higher convergence within the image. So if you slide them within within each position, you'll be able to get a value that connects to it. Right, so let me show you what that looks like. For example, in zero, if you slide each pattern over the image, you'll see where it overlaps, and that will be one score on that specific breed. And repeat this for every uh, for for the image, and then repeat it for the next pattern. And what you'll get is a score for every individual pixel, where you see a lot of convergence of the pattern. So what you get is a matrix of values that you can then move the next to the next to the next layer, right? So patterns that are good for zero do not occur for one. So each convolution layer should be able to check for this specific. The rectified linear units layer just converts negative numbers because negative numbers tend to balloon once you compute, and they are very computationally expensive. So you want to reduce them in order to remove outlying numbers, right? If there's a negative, particularly for convolution, where there is no matches, that often indicates that uh, that there is no occurrence of that pattern. But in most cases, that would mean um, that it's better to just set that as zero instead of leaving it as a value, because an absence, whether it's a lot of absence or just regular absence, will still hold true for our model. So here we're saving a little bit of uh, computation. And max pooling is the ability to sample down to the essentials here. So if we have 4 blocks within the same layer, the previous data has been passed to this max pooling layer. The result will be a 2x2 filter with stride length of 2 that is now able to hold a lot of the information that is within our data down to a uh, smaller size, and that way we can begin to make smaller and smaller calculations that will give us one specific value. And for classification, as opposed to the other types of uh, AI applications, there are just 3 layers that are very important, and these are always how classification problems end. One is the fully connected layer. So the fully connected layer, in essence, looks at high-level features and how do they connect to a specific category. So this is where the features of your architecture have now been extracted, and you now have a list or a matrix of values, and you want to then connect them to a set of classes, whatever the classes are or categories that your model has to predict, and be able to understand which those features are connected to which category, and calculates a score that each category is able to give so that you can order it. A softmax layer just divides this into probabilities according to this curve, and a classification layer just gives you the classification of the class with the highest score. So it gives you the final output. In converse to this, the other side of problem is for regression problems. Uh, for regression problems, you remove the softmax layer and just end to a regression layer, which maps it into a specific value. So how do you know which layers to use? So if you're doing feature extraction, particularly for images, you'll do a lot of 2D and 3D convolution, a lot of those transposed convolutions uh, in sequence with each other in order to extract specific features. You'll try different patterns, different strides in order to extract as many features as you can. Uh, in activation functions, wherein you want to make sure that your data is not being controlled by the operations. You'll do ReLU and tanh, or the hyperbolic tangent. For sequence data, if you're doing a lot of signal, text, or numeric data, you might use an LSTM architecture or a word embedding architecture. And often you'll want to do a normalization to make sure that your positive values never go out of whack, so that you change your biases between each feature. You want to do dropout and batch normalization layers. All of these layers you can actually input from within MATLAB. They are already pre-built layers that you can just call. If you're looking at for a specific problem, we have a lot of relevant examples within the documentation to see how each layer is operationalized. What are the inputs that are taken to them? What are the learnables that are being tweaked in order to understand it? You can also look at research papers from other sources in order to understand what each layer does and be able to use that as a guide for creating your own architecture. So really what you need to train any network is one, your data. How much data do you need? Well, it depends, but more commonly, it's always a lot. Because as you can see, uh, if you remember when we loaded the AlexNet, it had 60.9 million learnable values. And even discounting a lot of the feature extraction, your data set should be able to teach the model um, with your data points, right? So if there are 60.9 million data points, if you only have a few very small, uh, if you have very small amount of data, that is what we call under under specified problem. So if there are 60.9 million uh, learnables and you only have like 300,000 data points, you might not have enough data to teach all of the to specifically fit those 60.9 million learnables, right? And then network architecture is important as well. You have to define what are the specific inputs and what are the layers that you want to, and in what order you want to put them in. And then training is you want to check, you want to make sure that it's the right learn rate. So how often does it change specific values? How often does it check itself against the testing data? How many repetitions can it do before it gives up? When does it, what is the solver that it's going to try to solve? And you can actually keep track of all of those via the experiment manager. Right, so you can run a lot of the training sessions that you'll be doing by exploring those hyperparameters using the experiment manager, which is a uh, point and click tool now bundled within base MATLAB. And you can actually use this for a lot of your testing, not only for deep learning, but as well as for optimization, for parameter sweeps, for if uh, testing of large data sets. You can actually do experiment manager as well. So I know I'm skipping a little bit here, so to not show you what designing a network looks like. Um, but you can actually not have to train your own model if your problem is very specific. But if it's very similar to some other problem, uh, you can actually do what we call transfer learning. So specifically in this slide, this is an, let's say you're a ship, a dock manager, or a dock master, which is somebody who keeps track of all the boats within a certain dock or a certain port, or a port master, for example. Um, your job is to look at each boat that comes in, classify it in order to be able to make sure that your port has enough space for everyone. So all of the private boats that are just for sailing, the small boats have to be together. The large boats, the yachts, have to be together, because if a yacht is next to a small skipper, more than likely, if there's a sudden wave, the yacht will break the small skipper because of the size difference. So you want to be able to classify it, but you can't have one person just watch it all, uh, watch the watch the horizon constantly looking for boats and classifying them. It's better to just have a camera pointed, take a few photos, and then be able to classify it. So now we know that there are general application image classifiers, AlexNet, for example, GoogleNet, and those are very good at taking images and understanding what they are because they were trained on a very specific data set that had millions of images. But they're designed for general purpose. There are 1,000 classes. They have mugs, pens, cars, flowers, insects, pets. Those kinds of classifications are what are embedded into AlexNet, GoogleNet, and all those. But they're already trained well that they can pick up small features that correspond to those classes. So you'll see here in the pre-trained network, the last layers are specific to those tasks. So you'll remember that the last layers are the softmax layer and the fully connected layer. Those layers allow you to match features to the classifications. But the early layers are just for feature extraction. So it's a waste to have to retrain it from scratch. Instead, what you do is you take those last three layers, replace them with features specific to your data set. So here we're going to change it to a boat, different images of boats and different classifications of boats, and then train the new network that we now have done surgery on with our own training options. And instead of having to train millions of images for 1,000 classes, you will just need hundreds of images for like 10 classes or a little less on that. And then you can then get test images and run them through the trained network. And to do this, we're going to go through an exercise called food, and it's going to be uh, similar to the demo that I showed at the start of this session. We'll be taking through the food data and then classifying images within that data set using the transfer learning model that we will build. All right, so you can go to MATLAB again. Let me go up. Sorry. Go back to exercise files. So let me go to I'll skip 2 and 3 and then go to straight to 4. So you'll see here, let me double click on the folder so that we are on the right folder here. Obviously, I can open just the solution to transfer learning. If we are, I think we're a little bit behind, so I'll just go through it here now. Okay, so hopefully you can follow. Right, so the first section here is just, are you in the correct directory? So just make sure that the address bar points to 4, transfer learning, and just run this section just to make sure that it's in the correct space. And then the next step is just going to be loading a data store. A data store is just a file type within MATLAB that is used for handling lots of images. This just makes it easy to correct our data set. But you can do this. You can do this by point and click later in that. And here we're just going to look at what the data looks like. So here we're just going to take a random file. So this is just a random integer within the length of this file. And we're just going to take one random image and then just to see what that image looks like once it's loaded. Right, so you can click one section here. We just want to see what that image looks like. Right, so this is a pizza, and you'll see the label is actually what the image is. And you can run this section a few more times. And you'll see that how robust our data set is. Okay, so you'll see that it has a few different uh, different orientations of the images that are within it, even in the same category. So some of the pizza has been half eaten, some of the pizza uh, is taken from a different angle. And this represents a lot of the requirements for a very good model because you want it to be able to see features that are specific to the object and not specific to the data set that you have. So you want your if you're taking images, you want to take a lot of images uh, in different lighting, in different angles, in different color modes, in different saturations, uh, or yeah, and you want to, as much as you can, be as even with your data set as you can. So as many images of pizza as there are French fries, as hot dogs, as the other classifications here. So then the next step would just be splitting it into three so that you can get training data, validation data, and test data. So training data is the data that the model learns from. Here we're doing 70, 15, 15. Uh, More commonly, I'll see 70, 20, and 10, which is there is 70% of your data will go to the training, 20% of your data will be on validation, and 15 will be for testing. So validation is the data set that you use for uh, during the iterative training. So you always check your progress of accuracy on validation data, while testing data is for after training. So if you want to test the performance, the training model should never have seen this test model, this test data before. So, so now that we've run this, do not run the next section. Our next, our next, uh, our next goal will be to open the Deep Network Designer app. So here you can go to apps and you can actually just type Deep Network Designer, and you'll see it here, and you can open that. Right? And the Deep Network Designer has a start page. So if you have a network already in your workspace, you can import it that way. Or if you have a network that is uh, on from PyTorch or from TensorFlow, you can actually import that directly through this navigation. Here, I'll just open GoogleNet because it's one of the more relatively simple applications that we're going to see. Right, and then we're going to do a little bit of model surgery. I'll show you here, uh, and then change the output size just to from 10 to 5. So let me open this again. So yeah, so you'll see AlexNet was a simple network that has one line, but GoogleNet is a little bit more complex. So here we're just going to uh, zoom in. So to zoom in, you can just click Control and then scroll. MATLAB will automatically understand that where your cursor is where the center of the zoom should be. So here, what we're going to do is we're just going to remove these three layers. Actually, let me let me do a copy right next to them so that it's easier to move. So here I'm just going to add a fully connected layer. Then I'm going to create a new softmax layer. And then I'm also going to put in a new classification layer. Here, I'm going to change the output size of the fully connected layer to just 5. And then the classes of the classification layer can be set to auto. So here, I'm just going to delete the last 3 layers and just drag this directly here. And then set that as a dataset. Right? So that's our new network. I can then go to our dataset here and choose the image data store that we have. So I can choose whether if I already have the images labeled, I can actually choose from folders. But here I'm just going to use the data store already within MATLAB. So here I'm going to use trainds. And for validation, I'm going to use valds. You'll see here a few augmentation options that are present. This is basically a range of transformations that you're going to allow MATLAB to perform in order to increase the robustness of your workspace and allow it to learn a little bit more. So here I'm just going to import here. Directly, no augmentation changes. Right? So you'll see we don't have a lot of hot dog data, but at least in both validation and training, the amount of data is commensurate between validation and training. So here we're going to look at the data again, and then we're just going to set a few training options, which should be set here. We're going to change the initial learn rate to 001, validation frequency to 25, set it to 5 epochs, set the mini batch size to 32, and limit the validation patients to 3. So we're going to do that. So let's go to training options. I'm going to do SGDM as well. Mini batch size is 32. Max epochs is 5. Validation frequency validation patients is just 3. That's okay. Let me just check. Oh, 25. We have to limit it to 25. So 5. Okay, that's going to be enough. And then we're going to do train it. If you're asking specifically what each training option does, you can look at the documentation. But in essence, initial learn rate is how fast or how many iterations does MATLAB take before aggressively changing the value. So despite a slow initial learn rate, what we're doing here is it has to look at small changes and then go for the more drastic ones before moving through it. Validation frequency is how many iterations do you take before validating on the validation data and testing your accuracy. Max epochs is how many passes through the data do you go through before ending the training. And then the validation patience is how many testings of the validation data do you have to check before you're happy with before proceeding to the next iteration. So here we are really limiting a lot of the training that we're doing. We're only doing a total of 120 iterations within the data. That is, we're changing values for only 120 passes before we stop the data set. If you're not familiar with this graph, you'll see that the top part is labeled accuracy versus iteration. So you'll see that for each iteration, where each iteration is each epoch is essentially about uh, 25 or 30 uh, uh, iterations. That's where you want to check it here. So you'll see the accuracy is, or this accuracy is validation accuracy. So you'll see accuracy is steadily increasing, and it's actually increasing very fast, while the loss function is decreasing very quickly as well. So loss is a measure of how wrong each of your incorrect guesses are. So in essence, this is allowing a measure of when the model makes a mistake, how how far away is that mistake, or how how accurate are the incorrect guesses, right? So, for example, is it looking at specific features, and what was the confidence value for that specific guess? Was it very high, or when it was confident in a guess, uh, was it wrong? Those kinds of things, right? So, for example, if its confidence value in the softmax layer was 0.7, how that is a very high loss as compared to if its confidence value was like 0.5, for example. Right, so your deep learning layer is here as well. Right, so here within 3 minutes, we were able to get a validation accuracy of 95%. With a very small loss value, which tells us that this is more or less going to be a uh, very good model. And then we can then proceed to uh, export the trained model to a model named trained network underscore one. Right, so it's exported onto our workspace. So let me close Deep Network Designer. And actually, let me just minimize it. I don't really need to close it currently. And then we can then export the network here and then just rename it on this side. So here we're just going to rename it and then save it here. And then you can actually test the network. So we're just going to load it again and change the input size. And then we're just going to classify a few networks and then calculate its accuracy. Right, so our testing data set reveals that our model is actually closer to about 88.64. And then we can check the confusion matrix. So you'll see here confusion matrix, confusion chart, which tells us what the predicted classes are and for each true guess. Right, so along the diagonal, you want it to be as dark blue as it can be, because that means that it guessed a lot of these data to be correct. So you'll see for French fries, when the image was actually contained French fries, uh, the model predicted that it's either a hamburger or a hot dog, uh, which might be because a lot of images between hamburgers and hot dogs do contain fries with them. or maybe it's some correlation to the fact that a lot of these foods are served in the same restaurant. So maybe the model is looking at that. That might be what you might want to look at. You'll see that pizza is also being predicted to be uh, almost all types of them. You might want to look at why it's deciding that uh, sushi and pizza are very similar to each other, and you might want to look at that. Uh, Maybe your data set has a few overlaps, or maybe your data set has a few color corrections that need to be done, right? And then for hot dog, it's not a very good model because it's detecting hamburger here. So maybe it's the bread that is throwing off the model, right? So this gives us a few idea of okay, what does our data look like? Why is it looking at this like this currently? And then you can actually view some of the results that allow you to check it here. So here I'm just going to take a random image again, and you'll see the predicted label and the actual label being seen. And you can keep running this section just to check how often your model is correct. And you'll find that most of the time your model is going to be correct because it's very good with pizza and it's very good with hamburgers. And a lot of your data is actually of pizza and hamburgers, if you remember correctly. And then you can actually see then study the layers of the model and see how it's deciding what the correct one is. And you can actually look at the layer weights for each of them and see what they look like for each activation. So you'll see here the activations allow you to understand what are the features that are present for each convolutional layer. Right? So a little bit of perspective on what allows you to understand how your model works. All right. I hope everybody covered that so far. So we've gone through one, training a deep neural network from scratch. If you wanted to try it for food, you can actually try to build your own. Just use a convolution input layer, a convolutional neural network, convolutional layer, ReLU layer, and a max pooling layer, and then connect that into a fully connected layer, a softmax layer, and then a classification layer. And that's the most basic neural network that you can build, and then train your data on that and see the difference between doing it from scratch and then doing transfer learning. Right, so we've covered these two, where you can just fine tune a pre-trained model using transfer learning instead of using a lot of data to train a neural network from scratch. You can also do a little bit of deep learning in order to make traditional machine learning much more efficient. So machine learning models are very statistically significant. The bigger the more common issue is that extracting those features often takes a lot of effort in terms of having to go through a lot of data preparation or having to do a lot of image processing or signal processing in order to extract them. It One thing that you might want to do is machine learning models are easier to train, easier to implement. It's just a matter of extracting the correct features. So one way that you might want to do is to go through load the images into a pre-trained CNN, and from there just extract features that will be done by traditional machine learning models, whether it's SVMs, decision trees, um, and there be able to work together. So we have a lot of examples on this from MATLAB. You can look at image category classification, and then image extraction, image feature extraction, uh, listed in the examples. One common, obviously, classification is now a little bit outdated, and you can actually do a lot of the work that you'll see. A lot of the sorry, and you can actually uh, just load the models, and you can actually use your current cell phone to do classification on your smartphone through a lot of the built apps like the QR scanner, which is able to understand that there's a QR code within the image, but also the Google Lens feature, which is able to classify plant species, be able to understand locations, um, or and you can develop a lot of these AIs as well. And then the more advanced application today, and the one that is being developed still, is object detection. So classification of an image where there is one subject is very simple, but in most images that you see online or in reality, most images contain multiple objects. So the idea that just classifying one single image, one classifying into one category all of the parts of an image into just one label is getting a little bit uh, older, and that is where object detection comes in. Object detection is then a an evolution of the classification problem, where instead of looking at the whole image, you're looking at subsections of the image and being able to identify specific objects within them. So here you're able to detect the vehicles within the image. You can extend this if you want to be hyper vigilant to be able to detect as well. Okay, these are the trees. This is the road. This is a structure. Those kinds of things, right? And we do already have a lot of the deep learning examples that are present within MATLAB. You can actually use pre-trained models like Faster RCNN, YOLO V2, YOLO V3, single shot detector, and import them directly and have their classification placed within, and use them out of the box to detect images. And much like transfer learning, you can still do transfer learning with for object detection by just uh, training the models on new data sets. But you have to then label those new images. Much like our YOLO V2 detection, if you import a model, you just need to change the YOLO detection layers uh, at the end of the model and then train it with new network data. For that specifically, you can actually go through the so for that specifically, you can actually open uh, sorry. You can actually open the object detection exercise and go through the steps that you need to do uh, in order to understand what the data set is. You'll see that this exercise no longer has a an app-based workflow, uh, and that's fine. Uh, and we recognize that a lot more applications are coming. In the next release of MATLAB in 2024A, we are actually planning to incorporate a few of those changes and allow you to train object detection networks within the Deep Network Designer uh, GUI based application. So you'll see here there are a few steps I want to highlight here. One is you have to resize still the images, so you still have to split the data into training sets. Uh, and then you have to do two data sets. One is the image data store, and then the box label data store, wherein you have to wherein it contains not only the images but also the box, the labels of each individual item. And then this network you can do using uh, a little bit of code processing here. Right, so if you're curious about this specific topic, you can go through that exercise and try to run it to see what specific models changes. So so far we've just been going through image data, but your network architecture will depend on whether you're going through image data or if you have signal or text data. And what we found is that for image data, by far, the more common model architecture that you see is the convolutional neural network. While for signal and text data, particularly like in predicted anomaly detection in signals, like in seismic indicators or in predictive maintenance or in text analytics, we see LSTMs as the most common thing. So if you have any time series data, LSTMs seems to be the preferred network because of its speed, but also its flexibility of memory. While CNNs are able to look at data on a certain outside of the sequence. So the most basic sequence specific architecture is what we call recurrent neural networks. So for every if you have a sequence of data, new predictions are made because with accounting for the previous step, right? You use the new data, and then you have on hold over H2 that looks at the data and then updates it. So, for example, I had a if I had a sequence of words that uh, I had an essay that said I was born in France, and then I had 2,000 words of text at the end. I have to remember France in order to full out this, in order to figure out that the next sentence of I speak should be French, right? So you need to understand a little bit of long-term memory and not just the last value that you have. So that's where long short-term memory networks come in, where there is a state that persists throughout, and this state is updated as you go through the system. So it's not always the same system. Sometimes there are persistent memory steps that you need, but that state is very useful. And an LSTM network looks like this. You put in a sequence input, put in an LSTM layer, then take the fully connected layer, a softmax, and a classification output. For regression, you can just change this. You can remove the softmax layer and put in a regression layer. LSTMs can cover both classification and regression. Right, so this is very good because you're looking at a data set. The problem is if you look at the long short-term memory network, if you have a lot of data sets. Um, this It takes a lot of data in order to train it correctly. It's very good because this this architecture is very good with sequence data because it's able to understand it quickly. The problem is that you need a lot of data to go to increase your model, especially with signals that are very repetitive or signals that are uh, have a lot of confounding variables. So one way that you might also want to do is instead of using an LSTM layer that looks at the sequence, what you do is you create a convolutional neural network that looks at time frequency transforms. So CNNs are very good at images, and time frequency representations are often in the form of 2D images uh, that you can actually observe. So you can do this if you're not really familiar with the signal extraction or signal engineering that is common. And you can use this as a good starting point for signal classification applications. And there are a lot of time frequency transforms available in MATLAB, whether it's the basic spectrogram, the wavelet scaleogram, Wigner-Ville transforms, Hilbert-Huang, constant Q, or the perceptually spaced spectrogram. All of these give varying features and give are good for specific types of analysis wherein some data might be useful. I know that the Wigner-Ville transform is very good for communications data sets. The Hilbert-Huang transform is very good for uh, high frequency data sets. Uh, Basic spectrograms are really good uh, for medical images. Wavelet scalograms are good for communication as well. It'll depend on your specific use case, uh, what kind of frequency transform you might want to employ into your system. So if you look at the continuous wavelet transform, you can actually begin to break down, for example, this EEG record into a scaleogram. And if you look at the different types of ECG records, you'll see that you have a very apparent difference between this EEG and another EEG sample just based on the scaleogram itself. Right, so if you train LSTMs directly on signals, long signals subject to signal drift. So, for example, if you have a very long sequence, sometimes your LSTM will be able to get uh, signal drift, wherein uh, it's able to look at the state and then achieve 100%, and then suddenly flip to zero because suddenly it's learning too slow because it's learning this state embedded inside. And then training directly can lead to poor network accuracy. So one thing you might want to do is to do a little bit of what is called signal feature extraction, where you extract the features directly and then feed all of those features directly into your LSTM network. Right, and you can actually do automatic features extraction with wavelet scattering. So if you have samples that are 65,000 samples long, you can actually do feature extraction and reduce the dimension. Well, increase the dimensions, but reduce the sample length in order to allow the LSTM to learn better. So here we're going to go through the ECG examples. There are a few steps to this that we are going to work through. And we're going to go through the two parts of it. The first one is we're going to do a classification problem by transforming the ECG signals into a uh, frequency transform. Uh, and then we're going to perform a convolutional neural network classification on it. And then the next part is going to be taking the ECG signals, performing automatic feature extraction, and then taking that feature matrix and then training the LSTM network on it. So you'll see here, this is our data set. It's going to be ECG data set to classify three different things, three different conditions. One is the NSR, which is the normal sinus rhythm. So this is what a healthy sinus, uh, sorry, not sinus. Yes, S is sinusoidal rhythm. So, so here a normal system will look like this. And ARR means that it's under arrhythmia, which is it's elevated, but the recovery is not as good. And then with CHF, which is conditional heart failure or cardiac heart failure, which means that it's undergoing significant distress and the pressure is negative here. So we want to be able to make a model that is able to classify this data when it's fed into it in order to detect it consistently. So I'll go through the exercises using the solution parts and just explain what each block is doing in order to, as we go through it, so that you can understand. So let me go back to my MATLAB and open signal classification ECG. So I'll go through the ECG CNN first. And here, again, this is just a check to see if we're in the correct category. The first section is. And the next section is just going to be plotting what our data looks like. So NSR is normal sinus rhythm, ARR is arrhythmia, and then CHF is congested heart failure. Right, so this is what the dataset looks like. We have to create a model that's able to classify this easily. So the first thing that we want to do is we want to look at, okay, if we take just one image and subject it to a wavelet transform, continuous wavelet transform, what does it look like? So you'll see if it's a congestive heart failure data, CHF data, this is what a wavelet scaleogram looks like. So what does the NSR looks like? Right, so you'll see, okay, there's a little bit of pronouncement in this specific frequency at this specific time. And visually, with arrhythmia, you can see a little bit of a higher frequency and also a little bit of these lower frequencies as well. Right, so a few visual indicators that tells us that if we put this into a CNN, which is very good at understanding features and extracting them, is then able to exit this data. So then you can actually run the prepare signal data so that when it's processed into an image database, you can actually just take the data store here. So a lot of the wavelet transformation has already been created in 6 wavelets, and it's actually it's already in these folders in ARR, CHF, and NSR, so that we can train it similar to what we did with the food identification example. Right, so you'll see here, this is the AR prepping signal data. We actually removed the this data set here and just cut it at this specific junction in order to make it correct. Right, so again, the typical steps that you'd normally do, you split the data set, and here we're going to do a programmatic training. So you'll see here, we're calling SqueezeNet and we're calling the layers. And then we're just going to replace the final layers in LGraph here. So you'll see here we're removing the convolutional 2D layer, and we're also removing the classification layer here. All right, so a little bit of changes, but essentially what we did in the D&D app previously. And then we're just going to set a few options, and then we're going to train the network using and name it ECGNet here. Right. So in essence, we're able to see how it's trained and see what the steps are that we're doing in here. So again, what we're doing is we're extracting the layers. We're putting in a data store, and we're just augmenting it a little bit in order to change the input size when they come in. And then we're just going to use the find layers to replace, which is essentially a function that allows you to find the last few layers and then place it here. And here we're just going to create a new convolution layer and just replace it such that the number of classes is now the same, as well as the classification layer are now placed here. So this is just transfer learning of ResNet, and we now have the output shown here, right? So we have a very accurate model. In fact, our training gives us an accuracy of 100%. And if we want to test that with our test data that we reserved, you'll see that it actually is able to achieve 93.75% accuracy in our data set. Right, so that's applying CNNs for our for signal classification. So let's look at what happens if we go to LSTMs. So the first thing that we want to do is we want to look at the ECG data again. Let me just clear. We look at the ECG data again, and then we're just going to transform each one of those signals into a wavelet scattering. So wavelet scattering is different from continuous wavelet transform. Continuous wavelet transform produces a scaleogram that you can save. Wavelet scattering saves your signal into a feature matrix. So here, we're not only doing just wavelet scattering, which transforms it into a very long signal, but also we're transforming it into a feature matrix using the present wavelet scattering factors and the signal that we created. right? So here we now have instead of a sample signal that has 65,000 points, we now have just 492 by 8 matrix that we can then use. And then let me just run this first.